Now, let's turn our attention to fractals. In this lecture, I'm going to develop a new idea of dimension. It's called similarity dimension. And what we're going to do is we're going to take this idea that we've just learned about scaling factors and we'll turn it around in a certain way, and we can use it to develop this new idea. So here's how it's going to work. Here's an example. Consider an equilateral triangle, which is made up of 9 smaller triangles, as shown here. What I'm showing you is that if I take one of those small triangles and then 8 copies exactly the same and cunningly arrange them, I get a bigger equilateral triangle. And I use 9 pieces to do that. However, I don't get a triangle which I would say is 9 times as big. In terms of the edge length, it's something that's 3 times as big, and you can just see that. If you look along any edge here, you'll see in the big triangle, you'll see 3 of the edges of small triangles put together. So the scaling factor is 3. And yet it's taken 9 of these pieces. Well, we're not surprised. We knew this was going to happen. If we were going to be able to assemble any number of pieces to get this bigger one, it would have to be 9 pieces. Let's reiterate. 9 copies, and we've made something that's 3 times bigger. Now, how are these numbers related? Well, as we know, 9 is 3 squared. We've seen this already. This is just reflecting what we already knew about scaling factors. The scaling factor for area should be the square of the scaling factor for the edge length. So 9 should be 3 squared. However, we could think about turning this around. Suppose we weren't really thinking about dimension to begin with. Let me go back to this picture. And we just knew that to make something 3 times bigger, we had to use 9 copies. Well, then we could infer that we were working with something 2-dimensional. You see? Knowing that 9 is 3 squared, that tells us, because we have to use the exponent 2, that the dimension of the object must be 2. It may seem like a crazy way to do things. Of course, we know that a triangle is 2-dimensional, but here I'm showing you, even if you didn't know that, if you just knew you had 9 copies and you got something 3 times bigger, you could infer that you were talking about something 2-dimensional. Okay, it may seem like a kind of a weird observation, but we can apply it to other sorts of objects. Now let me give a name to this. If we compute a dimension from these 2 data, that is to say from the scaling factor and the number of copies, just as we've done, we call it the similarity dimension. In general, what do we mean by the similarity dimension? Well, it's the exponent that you need when you write the relationship between the scaling factor and the number of copies. That's the definition. It's the exponent that's needed when you write the relationship between those 2 pieces of data. For this triangle, again, we discovered it was 2. But now let's apply it to this curve that you studied in a prior recitation, the quadratic Koch curve. Remember, this started by drawing a square, and then each edge of the square was replaced by a pattern of 8 shorter edges, and then each of those shorter edges was replaced by a pattern of 8 even shorter edges, and so on. And this is showing you at least roughly what a quadratic Koch curve looks like. Now, this is a self-similar object. That is to say, you can look at smaller pieces of the quadratic Koch curve and you'll discover they're just other copies of the quadratic Koch curve. And I'm showing you in this example exactly that. So I'm showing you a big Koch curve, and I'm showing you a little one, which is a piece of the big one. In fact, how many of those little pieces do I have to put together to get the big one? Now that may be a little bit hard to see in the picture, but here's some help. And also I had a little bit of help from Microsoft in somehow managing not to overlay my pictures exactly where I want them. But those yellow dots are almost where I want, and they're good enough to show you how those 8 smaller pieces are laid out so as to make the bigger copy, the bigger Koch curve. In fact, the answer is 8. If you take 8 of those small pieces and arrange them as I've shown you here, you get the big piece. Okay, so to make the big curve, put together 8 copies of the little curve. Now when you're done, you won't have something that's 8 times bigger. That is to say, it won't be 8 times the length. If you measure the length of the little one from end to end, just straight line distance, then in the one on the right, the big one, that length has been multiplied not by 8, but by 4. So the scaling factor is 4. So here's what we've seen. If you put together 8 copies of the little curve, you get the big curve, which is 4 times as big. Now, we have to ask ourselves, how are these numbers related? How is the number 8 related to the number 4? Now, there's lots of ways to answer that, but we want to give an answer of the form 8 is what you get by taking the number 4 and raising it to some power. And the only number that will work there is 3/2. That is to say 1.5. After all, what does it mean to raise something to the 3/2 power? You can think of doing that in 2 stages. First, take the square root and then cube it. Let's do that to the number 4. If we take the number 4, its square root is 2, and then when you cube it, you get 8. So what I'm telling you there is really correct. 4 raised to the 3/2 power is 8. It's exactly the exponent that will work. Okay, all very well, but we're going to now interpret that exponent as a dimension. That 3/2 is what we're going to call the similarity dimension of the quadratic Koch curve. Let's try it with the Sierpinski gasket. So here is a big Sierpinski gasket, but as soon as you look at it, you can say, oh, there's 3 smaller copies there, right? There's a top one, there's a left one, there's a right one. There's not a copy in the middle, right? There's just a big hole in the middle. So if you want to make a big Sierpinski gasket, you have to assemble 3 smaller Sierpinski gaskets. You have to put together 3 copies of a smaller one. But when you're done, you get something which is twice as big. So 3 copies, and we've made something which is twice as big. Again, we ask, how are these numbers 2 and 3 related? What we'd like to do is to find an exponent, let's call it d, for which 2 to the d equals 3. Now this is a little bit harder than the previous one, because you're not going to find a simple fraction that works. Certainly d equals 2 is too big, and if now again you try 1.5, you'll discover that's also, wait a minute, it's too small. I was going to say it's also too big, but it's too small. What I'm claiming is if you take the number 2 and raise it to the power 1.5, it's not quite big enough. It's not 3. So somehow the number d that we're looking for, this exponent d, is somewhere between 1.5 and 2. Well, by guessing and checking, one could refine one's estimate. One could home in on the value of d. However, there is a shortcut, and here it is. What you do is you compute log of y divided by log of x. Here, x is the scaling factor, and y is the number of copies. So you do this seemingly crazy thing, but it's exactly the correct thing to do to figure out the exponent that we want in our equation. When I say log here, you can just think there's a button on your calculator. It's called log. Maybe you know something about that. Maybe you don't. It doesn't really matter. It is an important function in mathematics, but what you need to know is it's what's going to be used in this formula to allow you to find the exponent you need. If we try that here using the number y equals 3, that's the number of copies, and the number x for the scaling factor, the number 2 for x, the scaling factor, then we're going to get log 3 divided by log 2, and when you punch the buttons on your calculator and work that out, it's a little bit bigger than 1.5. It's about 1.585. That is said to be the similarity dimension of the Sierpinski gasket. So now what are these numbers telling us? Well, they're telling us that these fractals in some sense are in between 1 and 2 dimensional. Okay, so the quadratic Koch curve is so complicated and convoluted that it's not a one-dimensional thing. It's not really a curve in the sense that it's not a one-dimensional object. On the other hand, it's not a two-dimensional object either. It's not big enough or convoluted enough to be filling out something truly two-dimensional. Its dimension is 1.5, somewhere between 1 and 2. The same thing with the Sierpinski gasket, although it's not exactly the same number. It's not 1.5, it's about 1.585. So again, it's an object somewhere between a one-dimensional object and a two-dimensional object.